welcome to this online video lecture on fluid mechanics. So whatever concepts and numericals discussed in the previous video, hope you have understood all those concepts and numericals. Still, if you are having any doubts, you can comment them in the comment box and we will try to clarify your doubts. So today in this video we are going to start with a new concept, and further as the session goes we will solve some of the numericals related to that concepts. So without wasting much time, let us begin with this session. Hello my dear students, welcome to this online video lecture on fluid mechanics. So today in this session we are going to have a discussion on various energy losses in pipes. So during the fluid flow through the pipe, the fluid experiences some resistance due to which the flow of energy, during the flow some energy will be lost. So this loss of energies are grouped into two categories. So one is major losses and another one is a minor energy losses. So what are these major energy losses? So the loss of energy or the loss of head due to friction is termed as major losses. So it depends on the velocity of a flow, the diameter and the roughness of a pipe. So major losses are calculated by using Darcy Weisback formulae and Chesi formulae. By using these two methods, the major energy loss in the fluid flow can be identified. So whereas the minor losses are due to the disturbance in the fluid flow pattern. So these losses will occur due to the disturbance in the fluid flow pattern. So these losses means these loss of head are seen at various sections like sudden enlargement, then at the entrance of a pipe, at the exit of a pipe, sudden contraction, then obstruction in the pipe, bend in the pipe, then pipe fittings. So these minor losses will be observed under these condition. Under these condition, the energy loss will be observed. So today in this video we are going to derive the equation, that is Darcy Weisback equation, to derive the major losses. Consider a uniform horizontal pipe having a steady flow. So let D is the diameter of a pipe and A is the cross-sectional area. So let us consider two sections, that is 1,1 and 2,2, separated by a distance L. Now P1 is a pressure intensity acting at section 1,1, whereas P2 is a pressure intensity acting at section 2,2, and F is a frictional resistance at the surface of a pipe. So now the applying Bernoulli's principle to this condition or this flow, we have equation. By applying Bernoulli's principle, we have an equation between section 1 and 2 will be P1 by rho g plus V1 square divided by 2g plus Z1 will be equals to P2 divided by rho g plus V2 square divided by 2g plus Z2 plus loss of head due to friction. Since now from this schematic figure you can see that the pipe is already it is in horizontal position, means so the Z1 becomes Z2, and as the diameter of pipe remains the same, so even the velocity at section 1,1 and 2,2 remains same. So by considering all those conditions, I will get an equation P2 divided by 2g plus HF. So by neglecting Z1 and Z2 and velocities at section 1 and 2, I will get P1 by rho g will be equals to P2 by rho g into plus HF. Again, if I simplify this equation, I will get P1 minus P2 divided by rho g will be equals to HF. Okay. Now let us consider this one as a equation 1. Okay. Now as the pressure intensity is acting, means so there will be the pressure force. Now the pressure force acting at section 1-1, the pressure force acting at section 1-1 will be P1 into area, and similarly at section 2-2 will be pressure intensity at 2 and area, and the frictional resistance at the surfaces, that is F. F is a frictional resistance offering at the surfaces. Now if I resolve these forces in a horizontal direction and equate it to 0, so then it will be P1 A1 minus P2 A2. As it is flowing in the opposite direction, I have considered as a minus. Even frictional resistance will be in opposite direction and will be F, that is negative, will be equals to 0. Now P1, I will simplify this one, that is P1 minus P2 into A will be equals to F, that is F. Now whereas this F is a frictional resistance, so that is identified by experiment. I'll just erase this equation. F is a frictional resistance. Now this frictional resistance experimentally identified by the equation F is equals to F dash into area into velocity square, where F dash is a frictional resistance per unit area per unit length. So F dash is a frictional resistance per unit area per unit length, and area is a amount of area wetted, okay, and V is a velocity of a flow. Now this area can be written in terms of perimeter, so that is P into length, P into L. So in simple form I can write it pi d into L, okay. So I'll just replace this area, that is F is equals to F dash into P into L into V square, okay. Now if I equate, so I'll consider this as equation 2 and this as equation 3. Now if I equate this equation 2 and 3, so that is P1 minus P2 into A will be equals to F dash into P into L into V square. So then I will get equation, that is P1 minus P2 will be equals to F dash into P divided by A into L into V square. Okay. Now I have got P1 minus P2 equation. Now we know that we have already identified, that is P1 by P2 in the first equation. So that is P1 minus P2 by rho g will be equals to HF. So I can replace this one, so that is P1 minus P2 rho g into HF. So just I will replace this P1 minus P2 into rho gf. So that is rho g HF will be equals to F dash into P by A into L into V square. Now HF will be equals to F dash divided by rho g into P divided by A into L into V square. L into V square. Now P is a perimeter and A is a area. So I can simplify this one, that is perimeter is given by pi into D and area of a pipe is pi by 4 into D square. So if I simplify this one, I will get 4 by D. Let us substitute this P by A as a 4 by D, that is HF will be equals to F dash divided by rho g into 4 by D into L into V square. Okay, so let's take this as a equation 4 now. Now I have got HF equation. So now dividing and multiplying this equation, to this equation by 2g, that is HF will be equals to F dash divided by rho g into 4 by D into L into V square. Dividing and multiplying this equation by 2 into g. So I will get, so if I divide and multiply this equation, that is equation 4 by 2 into g, so I will get, so I will take this one term, 8 f dash g divided by rho g plus, sorry, into 4 by d into L into v square, sorry. Now if I divide this equation 4 by 2g by 2g, so then I will get it, HF will be equals to 8gf dash divided by rho g into L by d into v square by 2g. This equation is obtained by dividing and multiplying the equation 4 by 2g. Now again, if I simplify this one, okay, if I simplify, and we know that F, that is frictional factor, is given by 8f dash divided by rho g. Okay, 8 frictional resistance is given by 8f dash g divided by rho into g. So let us replace this equation and erase these steps. Okay, so this is a frictional factor. This is a frictional factor. Now HF will becomes F LV square divided by 2GD. Now this is Darcy Weisback equation. Now this equation is used to identify the major losses in the pipe. So this 8GF dash divided by rho g is a frictional factor. Now this question is asked in the examination, in the university examination, for 8 to 10 marks. Derive the Darcy and Weisback equation, or derive the equation for major losses in the pipe. So it will be asked for 8 to 10 marks, and even the numericals will be asked on this equation.